My name is Pinit Golamnichia. I'm co-chair with the lady here.
So I'm Palanchaya Jamkajang from the College of Sports Science and Technology, Mahidol University.
As president of SMAT, I would like to welcome you all to Hua Hin, Thailand. Thank you for coming. It's my pleasure today to introduce to you Professor Gareth Irwin, who is now head of sport and exercise biomechanics and co-director of the FIFA Medical Center of Excellence for Medical and Performance Center. He graduated BSc in Cardiff Metropolitan University, University of Wales at that time, I believe. And later on, he did PhD, and he is or used to be president of the Fellow of the International Society of Biomechanics in Sport. He has held many important positions and still has many positions to do, including visiting professor to Czech Republic and Mahidol University and many others. I would like to welcome you to listen to his keynote lecture on from skill development to injury resilience, understanding load, technique, and adaptation. Please welcome Professor Gareth Irwin.
Good morning, everybody, and thank you for that kind introduction. I'd like to firstly start by thanking the organising committee for inviting me here to give this talk. It's a great honour to be able to come to Thailand for my third visit and share some of the research experiences that I've had over the last 30 years. In giving this talk, I want to talk today about movement and technique, but not as a fixed performance model, but as an adaptive solution. I'm going to give some examples across football and rugby and athletics. But probably the most important part of the talk is the theoretical framework that glues the coach, the elite athlete, and the clinician together. And I'm going to try and use that as a golden thread throughout the talk. So the examples that I give are going to be from research that we've done in Cardiff and across different universities around the world, clinical and performance-based research, and the development of this framework. So starting with this coaching and clinical biomechanics interface, the aim of this topic is to bridge the gap between the underlying biomechanical parameters that determine successful performance. It's one of the key parts of coach development, understanding technique, and from a clinical perspective, providing information that the clinician can use to understand how rehabilitation, to understand how clinical intervention can work. And it's been a challenge for sports science and sports biomechanists for decades. With the athlete's well-being at the centre of this, our aim as sports scientists, as coaches, as sports medics, is to prepare, nurture and develop our athletes so they are robust, adaptive, primed and self-aware, so that when we come to treat, when we come to coach, when we come to intervene with the performers, it's individualised, it's safe, effective and efficient. Athletes are training near their physiological maximum. So understanding technique and understanding performance is a desired outcome. But as we know, human movement is not prescribed. It emerges from a confluence of constraints on action. And biomechanics provides a means to understand how that adaptation occurs, and also then provides a mechanism to understand how loading occurs and consequently injury risk. And the model I've put up is Carl Newell's model of constraints. Professor Carl Newell from Penn State developed this in the 1980s, and it's been one of the foundations for a lot of sports in the UK to understand and explain technique. And it explains the emergence of movement through this idea of self-organisation. The idea of the constraints approach is that there are three factors that really influence performers trying to achieve a performance outcome. So it doesn't matter whether it's football, and England won last night, or whether it's athletics or gymnastics, but the three constraints are the athlete, the organism, the environment, and the technique. And these are continuously interacting. The technique being the movement patterns, the body shapes, the coordination that is being performed, the athlete, the biological system, their physiological, psychological, and to a certain extent, sociological characteristics, and the environment in which they're performing, all interact to achieve a movement goal. And that movement goal could be anything from performing a simple skill like a forward roll in gymnastics, or more complex movements like penalties in the World Cup coming up. The interaction of these three constraints leads to this idea of self-organization. This is where technique emerges. It's not about a fixed model of technique. That technique needs to be adaptive. And as we change the environment or we change the athlete, the time of day that they're performing, fatigue, the equipment, the apparatus that they're using, the turf that they're performing on, the gymnast, the footballer needs to be adaptive and responsive to those things. So we need, as sports scientists and as clinicians, to understand how this self-organization process works. The coach provides feedback, and the factors that we're interested in that have a direct effect on performance are the coordination, the relationships between body segments, the variability of that, and variability being a functional characteristic, adaptability and stability of that variability. So this is the model that I'm going to put up a couple of times throughout the talk. And I'm going to give a couple of examples now from some research that we've done over the years. And I'm going to start with this one. It's this part of a number of papers that emerged from our group in Cardiff, and was part of a talk where I was invited to the Royal College of Surgeons to give a number of years ago. And it's about the influence of the environment, the influence of the boot undersurface, and the injury risk factors associated with that. So to put it into context, in the early 1990s, blades were introduced in football boots. Studs, the traditional stud was being replaced, and the blades became an alternative. They were cutting-edge technology at the time. They were talked about as in terms of enhancing performance, and big companies, big shoe manufacturers really pushed them. Stability, surface traction, comfort were all things that they were talked about. But injury fears quickly emerged. Coaches, players, medical staff, and several clubs, several Premiership clubs banned the use of blades for a number of different reasons, either micro-traumatic or events or other types of injuries. The English Football Association sent a dossier to the FEA, to the FIFA. The English Football Association sent a dossier to the world governing body of football, FIFA, sharing their concerns. And FIFA's response at the time was that there's no evidence or research-based evidence to indicate that these boots are more unsafe or produce more injuries. And it was the fact that there was tacit knowledge that there were concerns emerging and there was no real research behind it. So an orthopedic surgeon, Dr. Kalir, undertook a series of studies to examine this. When you look at the different types of boots, there are a plethora of boots available to players, to football players. The current materials are lighter, less than 250 grams, they're more durable. The configuration of gripping surfaces varies between models and manufacturers. The manufacturers have labelled the boots, and more so nowadays. Plastic, synthetic, plastic studs used for firm and synthetic surfaces are 3G surfaces, and deeper metal studs for softer and wet surfaces. However, the variability of playing surfaces currently in elite soccer on grass and artificial turf, and even across natural grass, means more research is needed in this area. And there are really three categories that the injuries associated with blades come into: lacerations, compression, and underlying technique. And it's the technique aspect that I'm particularly interested in. In order to address these questions about technique and how different boot undersurfaces affect technique, sports biomechanics places itself well in order to understand this from an injury and a performance perspective. Both these areas of biomechanics raise different questions. From an injury perspective, epidemiological evidence of what injuries occur, what are the injury mechanisms that occur, and can we identify the factors affecting injury? And then can this be useful in terms of rehabilitation and performance? The other aspect is, what is successful technique? How individual is it? How common are the movement patterns that occur and the variability? Can we explain what the key performance variables are? And then how can we optimize performance? Using our knowledge of mechanics and biomechanics, we can start to understand what the movement patterns and the coordination of movement is, either locally at specific joints or globally in terms of more macroscopic variables, for example, lean and stability. But we're also interested in not just the movement pattern, but the musculoskeletal loading, the demand on the performer, and how these musculoskeletal demands can create injury risk within certain skills, and particularly within football. We are interested in the kinetics at the ground level in terms of reaction forces, the rate of these reaction forces, but also rotations, internal and external moments, and of the joints. We use a variety of methods, including inverse dynamics, to calculate these forces, these torques, and the work being done by the performer. Back when I gave this talk, the technologies available were not the ones that we have nowadays. So this was probably about 10 years ago. With the emergence of markerless tracking, with the emergence of, and I know at Mahadum University this is something that they're looking to invest in, the ability to undertake this research is limitless. But the key thing to biomechanics and the key thing to understanding injury and injury risk is identifying the cause and effect of injury. And this is a very difficult thing, particularly when you're examining a performer from the outside in. We know the geometry of the performer and the variability of the performer is particularly interesting. And a reduction in variability is a cause for concern. Impact forces, rate of force development, internal and external forces all contribute to injury potential. But we need to take into account the playing surface, the movement, for example, cutting, and that was the skill that we looked at in this study, and whether the boot undersurface also makes a difference, the blades or the studs. There are a number of different research approaches we can take. They can start with epidemiology, understanding the injuries, and the occurrence of injury within an elite sport, for example, and particularly in football. And we can take an experimental lab-based approach, or we can take a theoretical simulation modeling forward dynamic type approach. A combination of these is probably the answer to this. Epidemiologically, in terms of boot undersurface and using different turfs, there's been a plethora of research from people like Ekstrand and Fuller, some of the great names in this area, comparing natural turf with 3G turf, looking at seasonal influence, the effect of previous injury as a risk factor. There have been a number of studies that have examined different playing surfaces and different boot undersurface. Some of the classic studies have looked at the frictional, torsional resistance and how this may affect the etiology of injury. Foot fixation caused by materials, the size of the studs, the number of the studs, blades. These are the things that players have to answer themselves unless they've got specific support. I'm pleased to inform you that the work that I've done in Premiership football and in World Rugby, there's a really good close relationship between both the medical staff, the sports science staff to address some of these issues. But some of the classic studies, for example, Martin Shorten's work, a very famous biomechanist from the US, did the initial studies looking at differences between AstroTurf astro play and field turf within American football, identifying that there were differences across torsional resistance, particularly with field turf and particularly with this astroturf, which is the old-fashioned, just a thin layer of carpet on the ground, which originally was used in the UK in the 1980s and was really known for bad friction injuries and these sorts of things. Probably the biggest leaps forward, though, in terms of understanding this area is the need for human subjects and real data. This information was collected with things like Clegg hammers and artificial athletes. Groups like at the University of Western Australia with Thor Bezier and the McLean at the Cleveland Clinic in the US introduced a number of studies that looked at athletes performing, soccer players performing these cutting movements across different surfaces, looking at loading of the knee, anticipatory effects, and the association to specific injuries. Other factors such as muscle tuning and muscle activation, for example, the difference in 100% increase in EMG during non-anticipatory effects in cutting in soccer. The Cleveland Clinic compared gender differences in players with an obvious increase in female injuries that has been present in football for many years. Decreased variability and increased knee valgus being two common factors of knee injury. These studies all led to a series of questions then about this real cause for concern. And it was Hall and Rue who identified that research was needed in this area and we needed more case evidence relating to stud awareness for players. So we started by undertaking a series of studies. And I'm just going to give you a snapshot of one of those studies. So Dr. Raj Kalia, a orthopedic surgeon from the UK who worked with the Welsh football team as a member of their medical staff. This research was presented at the British Orthopaedic Association, ACSM, International Society of Biomechanics, and also was produced a number of different papers, one of them being the paper in the American Journal of Sports Medicine. So this study that we did looked at the influence of the boot undersurface, specifically at knee internal and external rotation during cutting in football. As we know, the undersurface and foot fixation increases injury risk, and particularly internal and external tibial rotation plays a major etiological role, and particularly when knee flexion is occurring at the same time. So the aim of this study was to quantify those knee moments for elite soccer players, comparing running and cutting with different boot undersurfaces. And the question was, what are the musculoskeletal demands during these changes on FIFA regulation surfaces? So we had 15 subjects from 2 Premiership football clubs in the UK. We had a series of studded and bladed boots provided for us, which each of the players used individually. Each performer did 3 to 5 trials of straight line running and then sidestep cuts at 30 and 60 degrees on a FIFA regulation 2-star FIFA turf with approach velocity in the region of a common 5 to 6 meters per second. The data was collected in our biomechanics lab in Cardiff, where the athlete moved down the track and then cut off at different angles. And we used a variety of common biomechanical equipment to calculate, in this case, we calculated internal and external rotation, extension and flexion moments, and valgus moments, but we were particularly interested in the internal and external moment. And we were interested in it through the stance phase, So we examined blades versus studs and the differences across 3 different cutting positions. And then also, was there a difference between the blades and studs at each of those conditions? So a quick snapshot of some of the results provided us with, this is a common internal rotational moment curve for the 4 different boots, and the peak internal rotation occurring mid-stance. The key finding was that there is a significant difference in the turning forces at the knee dependent upon this anticipated cut, particularly as you would expect between 0, 30 and 60 degrees for each of the different boots. At the top here you can see the different boots that we used. Interestingly though, when we compared the different boots against each other, there was no significant difference. So the boot itself wasn't contributing to the difference in condition. And it was at this stage recommendations in terms of equipment was used. So there was a significant increase in the cutting angle, but there was no difference between the boot undersurface. So the kinetic demands didn't change. So the patterns of internal rotation were similar to those of McLean and Bezier. We reported moments are lower than the Searing's work, although Searing's work was actually on cadavers, so which was examine the critical limits of the knee and its structures. And self-organization was dependent on the task of cutting rather than the boot undersurface. So it was the task that was changing the organization of the movement. It wasn't the boot undersurface. So understanding that and understanding how that it changes per player is a future recommendation from this work. So boot undersurface was not found significantly different. But nowadays, kind of certainly in the last 5 years, there's been a tremendous personalization, individualization of boot undersurfaces. And athletes can change the different undersurface with a combination of studs and blades. So understanding those factors of the geometry of the performer, the internal and external forces, and also the pressure distribution becomes particularly relevant. And understanding the factors that we've looked at, playing surface, technique, boot undersurface, but also things like the game-specific demand, climate, fatigue, and importantly, biological variability, and how variability affects performance and injury. And this brings into other theories such as the dynamical systems theory. So importantly, from constraints to performance, as I put up before, we've got the environment, the task, and the organism, or the athlete. From that, coordination and functional movement solutions occur. And it's during those functional movement solutions that are individualized per person as a process of self-organization, that loading, that individual loading. And that's probably one of the most interesting findings from some of the football work that we've done at the moment, is the huge within subject difference, particularly with adaptation between different surfaces and different playing conditions. And having that brought into a clinical setting, and then having that brought into a physical preparation setting for prehab and for rehab. So I'm going to move on to my next example, and sticking with the theme of football, but now including another sport, rugby. I'm from Wales in Cardiff, so rugby is a very common and very popular sport in Wales, although in the 1970s we were very famous for it. Not so much at the moment, we keep losing, but we are still in the World Cup, and England did win last night, so everything's okay at the moment. So our work with turf has gone on for about 15 years. We have our own FIFA Medical Centre of Excellence at the university, and we've done a number of different studies. I just put four that I personally led. The technique analysis on 3G turf, looking at injury and performance and temperature and how that affects the human interaction. Interestingly, when the air temperature is 30 degrees when we were doing it in Spain, the ground temperature was about 45 degrees. So issues associated with burning, etc., were quite significant. Although, as I believe now, in the European Union in 2028, the rubber crumb is actually going to be banned as a microplastic. So alternatives to those are being sought. So we've done a number of studies with World Rugby, with our other colleagues at the German Sports University and Cardiff University. And the one I'd like to talk about briefly is player perception. So a number of papers emerged from this area in terms of the influence of artificial turf. And this player perception is a real interesting idea of how to undertake research. And it really nailed home for me the importance of interdisciplinary research, and in terms of understanding how we work as elite performance groups and working together in interdisciplinary teams rather than our monodisciplinary isolated selves sometimes. So there was a real push from FIFA back in around about 2012, and there still is, and World Rugby and other sports, to increase the number of artificial pitches, particularly from a social and economic perspective, because it allowed countries to not have to continuously water the grass, maintain the grass, not just at the elite level, but also at more of a social and community level. The benefits were really promoted, and it got to the point that the FA chairman, Greg Dyke, back in the day, was saying how grassroots football in the UK, because of the weather, because of the bad conditions in the winter, training wasn't available. And if you compare a country like Germany or the Netherlands compared to the UK, they have about 60% more artificial turf than we do. So they're able to train throughout the year. So it was an important thing, certainly from a UK perspective. 3G turf has been used at Women's World Cup. It's been used in rugby at World Cups, and it is becoming more and more common. But there are lots of issues. And some of the pictures that you see at the bottom, this was Wales playing Macedonia about 10 years ago. And you can see the rubber crumb spraying up from the ground. And there was a real issue around it. Coaches did not like the artificial pitches. It's the worst pitch in the world. Gareth Bale, one of the famous Welsh players, really bemoaned it. It's the worst pitch he'd ever played on. I can't describe how bad it was. It was a hard pitch to deal with. So if you're trying to sell a product like FIFA were, and you've got world-class players saying these sorts of things, it's bad publicity. And complaints from top female players in terms of why are we the guinea pigs having to compete on these things. So our research and the history of artificial turf, the first artificial turf was in the Astrodome in Texas in 1966. It was used in American football, which isn't really football. And it was in the 1980s that it was introduced into the English game. Clubs like QPR used it. Back in the 1980s, the ball was it was like playing on concrete. The ball was bouncing everywhere. It wasn't sustainable. And the players back then, and this is something to remember, the players back then are now the managers now. So they have a real ingrained understanding of artificial turf. Even in the 1990s, there were inconsistency in quality and safety. So all pitches in the English Premier League were replaced by natural grass, and it wasn't able to be used anymore. But FIFA and UEFA in the early 2000s really pushed to develop an industry standard. And FIFA then started using artificial turf in the Under-17 World Cup back in 2003. And the system of FIFA 1-star recommended and FIFA 2-star, the pro quality pitch, emerged later on that decade. And just to clarify what we mean by artificial turf, at the top here, this is 1G. This is what QPR were playing on, the first 1980s pitches. It's like carpet. It's friction burns, really, really common. The ball bounces everywhere, hard to run on. 2G, they started putting rubber crumb in it. It became a little bit softer, more grass-like. 3G, there's a shock absorber, followed by rubber crumb and sand intertwined into the yarn. Often you'll see clubs, certainly in the UK, saying that this is a 4G pitch. 4G pitches don't exist. The 4G pitch would be something if we invented another one. But at the moment, it's just shock absorber, infield grass. Commonly now at the Premiership level and at world level in rugby, they have another system called a DEXI system where natural grass and artificial grass are used together. So in Twickenham and Wembley, those are the sorts of pitches that the players are using. So we were approached by, I'm going to move across some of this. We were approached by FIFA and World Rugby, and we had a challenge. They said to us, we want you to compare players running on and performing on different types of surface, artificial and natural grass. But what you have to do is you have to not let the player know what they're running on. We want you to use elite performers, Premiership football players. We want you to use elite rugby players. So there's a place in Wales, just outside of Cardiff, where Cardiff City play and train, and Welsh Rugby play and train. Ideal venue for it. But the challenge of how do you stop somebody from knowing what they're running on? You can't turn the lights off and say, okay, run on this grass or run on the... They would know what they're running on. What do? Do you use smoke and make it so that they can't see what they're running on? Well, originally we were going to look at blind footballers. Interestingly, in the UK, we have a very high level of blind football. But they compete on a completely different surface again. So again, ecological validity, would it have been the same? So we had to come up with how we were going to examine player perception and performance on these two different conditions. And strangely enough, and this is published, strangely enough, what we found was the most effective way of doing this was for our population of elite performers, we removed as much bias as we could. So we degraded their perception, their visual and their audio and their smell as well, because it smells different. So we used earplugs so they couldn't hear what they were running on. We used nose clips so that they couldn't smell what they were running on. And then we went through a series of acclimatization to running with a blindfold on. But then we had the other problem. One, running with a blindfold on is particularly difficult. You can't shout to the person to stop because he can't hear you anyway. So you had to give them instructions, run 10 paces, turn around, run back. But they know where the pitches are. So this was the facility. Cardiff City play and train over here. This is an artificial turf. This is a natural turf. But they know where they are, so they'd be able to perceive where they are. So we put them on the back of a golf buggy. There's a really big, it's near Celtic Manor. It's a really big golf course here. We put them on the back of a golf and drove them around with a blindfold on, so they didn't know where they were. These are elite performers now. And if anybody's worked in elite football, you know how difficult those participants can be. So it was a challenge for us. So they got to the start of a movement task, which basically involved them running and accelerating for 10 steps, turning, accelerating back, and then cutting to the left. And they did that on artificial and natural surface. We used biomechanical equipment to measure movement patterns, contact time, step length, angles at the knee, hip, and ankle. And interestingly, we also used psychology, a player perception questionnaire and interview. So we had a psychologist working with us. And I'm going to jump straight to the results. What we found was that actually during the acceleration and deceleration phases of the movement, in the artificial grass, there were longer contact times and shorter flight times. So the artificial grass was producing a different movement pattern and movement solution. The difference in grass, though, between the two natural turfs may have contributed to those differences. When the performers were turning and when the performers were cutting, certainly when they performed the turning effect, there was no effect between the different surfaces, but in terms of any of the biomechanical variables that we were looking at. But in terms of some of the cutting movements, the artificial did have a shorter contact time, had a slightly higher level of stiffness. The psychology characteristics looked at player perception using a technique acceptance model and pleasure and arousal model, as well as some cognitive interviews, which is pretty rare in biomechanics to have this combination. And this is where it became quite interesting. The perception, when it was degraded, they couldn't tell the difference between the surfaces that they were running on. And there was no difference. But when we did it, so we did it with perception taken away and without. But when they knew what surfaces they were running on, they said that there was a difference. They indicated that the artificial turf wasn't as good as the natural turf. They indicated that it was too hard, they were feeling jarring and joint pain, and that the artificial turf didn't respond. But when they did it with not knowing what they were running on, those factors didn't affect it. What we found was that the bias, the pre-existing bias, was the main contributor. So those players back in the 1980s that are now the managers were having a huge effect on the players in terms of their acceptance of, and through their experiences of, artificial turf. And it had a really impactful, had a really big impact on the players. And it highlights that interaction between coach, player, sports science support team, and how that interaction can be very difficult. I'm going to jump onto my final example now. And this was a really interesting piece of research that we did. And it brought together our colleagues in Germany and ourselves. And we were interested in not if the environment changes, the grass, the boot undersurface, but what if the biological system changes? It changes every day, time to time. My biological system is different from when I started this talk to now. But what if there's a major biological difference? So, for example, in sprinting. So 2012 Olympics, athletes with unilateral amputation, bilateral amputation, and other disabilities performing in the Olympic Games in London. You can see that the differences in the movement patterns, the differences in the techniques emerging as the performer sprints. From the work that we'd done previously with elite performers, with people like, this is Darren Campbell, the Olympic gold medalist in 2008 and silver medalist in 2004. Our understanding of what makes elite sprinting and how technique evolves is fairly well understood. We had a group of, we had the opportunity to go to Jamaica and collect some data. And this is a graph of normal average horizontal block power. So that's a real significant, it's a really high correlation to successful technique. And this horizontal block power was used to profile the athletes of the Jamaican national team at the time. So all the little blue dots are the males and all the little red dots are the females. On the horizontal axis is the personal best. So this person over here, about 9.8 seconds, this is Usain Bolt. And then this is the rest of them. And it's interesting to see there is a clump in the middle where males and females are running at similar speeds. We know that the ground reaction forces during the start, ground reaction forces during the initial acceleration phase are particularly important. But as you can see here, these are the groups of athletes performing. The grey lines in the background are the variation of one performer performing it over and over again. So within subject variation is quite high. But you would expect that in elite performance, that variability would be higher in elite performers. You can ask me a question about that if you want to. We know about the importance of the knee joint and the ankle joint, but obviously during an amputee sprint, you don't have a knee joint if you're a trans femur amputee. So you don't have that ability to swing the leg forward. So you don't have that initial ground reaction force. Another interesting graph, again, horizontal power during the block. But this time, we've got the same graph, Usain Bolt up here on the left. But now we've got the transfemoral unilateral amputees, transtibial unilateral amputees, and bilateral amputee as well on the same graph. And you can see that the transfemoral unilateral amputees were actually the fastest, or this one was. This data were the Olympic team in the German squad. And some of the data that we found were the differences in the performer's ability to, particularly in the tibial bilateral amputee, the ability to bring that first knee up. So understanding how these athletes self-organized because of their changes in the amputation, the differences in the blade showed significant differences. So coaching, physical preparation all had to change and all had to be specific to the individuals. This is quite an interesting figure. It's a snapshot of just of two performers, one bilateral above knee and below knee. And you can see the above knee in the top figure having to swing his leg out to the side, loading his hip joint more because he doesn't have that knee. Having the knee joint in the bottom figure allows the person to lift the leg up and drive further forward. So from a physical preparation and distribution of loading, it became a particularly important thing for this person to understand how that technique that was emerging had a specific loading effect on it. So as the person self-organized, the impact on loading, because of the degrees of freedom, was significant. So the practical value of biomechanics isn't simply about measuring movement. We can measure lots of different things in biomechanics, internal and external forces. We can measure, and it's a real bugbear of mine, that it's not about measuring things, it's about interpreting how our athletes adapt and using that to understand and support physical preparation and understand injury resilience. My final few messages really are: sports science and sports medicine requires a variety of approaches, ranging from theoretical to in the field, but ecological validity is important. Embracing the challenge of interdisciplinary research, working together as groups, is vital. It's something that the UK Sport Institute, it's something that certainly at professional sport level, I'm pleased to say does happen. Addressing research questions from a question-specific perspective. Just because I'm a biomechanist doesn't mean I don't need to have a psychologist, a clinician, or a physiologist with me. We're still limited by technology. There's limitations in everything that we do. Understanding those is the key. So trying to make statements about causal links can be dangerous. Incorporating other sciences. Probably some of the most valuable stuff I've done has been working with for example, Bill Gates' lab in Cambridge and the computer sciences. Working with the Royal Veterinary College on understanding human movement. So collaboration with the right people, and by that I mean people that you get on with, people that are kind. Making strategic alliances to address meaningful questions is really important. So I'd like to thank you for the opportunity to speak today. And I hope some of that was useful, and I'm happy to take any questions.
Okay, thank you very much for Professor Garrett Irwin for very good talk and very interesting research that you show to us. I think I'm sure it's very useful for all of our audience, and I'm sure we might have some question to ask the professor.
Dr. Paisan Chandrapitak, the chairman of the medical committee of the FA Thailand and also AFC medical committee. Thank you for your information, your research. In terms of the practical point of view, let's say we're taking care of the national football players for more than 200, 300 players. How to recommend them? Because we don't have the football boot specialist in Thailand. Or I don't know, even in other countries, do we have the specialists to take care? The second point, I think they get used to their boots for many years before they become the national players, and very difficult to recommend them to change from this brand to another brand or whatever, because a big conflict of interest. Most of them are the presenter of the booth also. I would like to ask how to recommend them or for practical point of view.
Thank you for your question. Excellent question. And it is difficult because some of them are sponsored by those boot companies as well. So, and we don't have specialists in boot design and recommendation. From my experience, the most important thing is that the players' adaptability isn't affected. So without giving away too much, and it's with the work that I'm doing with professional football, we're allowing players to wear the boot that they feel most comfortable in. And knowledge now about blades and deeper studs is quite common. And players have got to that level. And I think boot undersurface isn't the major issue anymore. I think more of the issue is the player's ability to adapt. And there are practical ways of doing that. 200 players, for example. That's a lot. But looking at a screening process where you can use very simple measures now, which come from video type data, open cap, these sorts of things, open sim, that don't require complex biomechanical equipment, can profile a player throughout the season, giving you a baseline and seeing, as that person fatigues, are there spikes in their ability to adapt? Are there spikes in their ability to cope with the fact that we're going to play in this surface in one game, and we're going to go and play in this surface on another game, in a cold November in the UK, or a hot, humid climate like we have here in Thailand. Ensuring that the athlete has that ability to adapt is more important than the boot. So coaching and physical preparation that embeds that in their training would be the first level. Making sure that they have a plethora of training environments. But at the higher level, I would say specific profiling. So we're looking at, with the club that I'm working at the moment, we're looking at profiling athletes 4 or 5 times throughout the season, trying to identify where there's changes in the variability of the performer. So are they stable athletes performing cutting movements on this turf? And then in the next testing session, there's sudden changes in that variability of movement. So, and then we test them again maybe a month later, and that variability is even worse. So then you say we need to do an intervention now to maintain this, because that's kind of predicting where the injury is going to emerge from. I'm kind of trying to answer your question, but it's about, in the first instance, physical preparation, and in the second instance, having some form of screening. Yeah.
Okay, thank you. Another question for this World Cup. Why most of the players choose the boot in pink color?
Yeah, I know. It's and everybody's wearing them. Maybe it's because they're pretty, but England won't be in it after Mexico anyway, so it won't matter.
My name is Dr. Yidror Prayun, orthopedic doctor from Thailand. Thank you for a very, very wonderful lecture. Since you talk about artificial turf, may I ask you a question that I concerned? Many years ago, there is some debate about cancer risk and artificial turf from the layer of and under the surface of the turf. Is it still a debate for that, especially for children and the goalkeeper or the rugby player who face is on the field?
It's an interesting question, and I've had the same question previously. It's an important question, and it has been in the press that probably, historically, it's not been in the press so much lately, but is it a carcinogenic effect of these artificial turf? The rubber crumb that we use, certainly in the UK, and I think quite commonly, is reconstituted tyres. It's not healthy stuff. The issue that was reported was about actually swallowing and that type of things for goalkeepers, and particularly in rugby when you're diving onto the field and it's in your face. And there's no, as far as I understand, there's no clinical evidence to show the causal relationship between, certainly the rubber crumb and those sorts of lesions or illnesses. But it can't be argued that it's a healthy surface. It's not, it is rubber, and particularly in climates where it's hot. One of the main reasons to have this turf was so that it could come into a climate like this, and you wouldn't have to water it. It would be able to be used for multi-sports and elite level sports. I think there's certainly alternatives to this rubber crumb, which is going to happen now because it has to in Europe, and that may affect other countries as well. But to answer your question, I'm still not aware of any evidence to suggest that there is a causal link. But it is my personal opinion is it's reconstituted rubber tires. So I don't think. My son's school, they use an artificial turf rubber crumb, and he comes home and it's in his shoes. It's everywhere. It's in his bag. They go and run on the field. It gets everywhere, and it can't be healthy. It can't be healthy. But I don't think it has. I don't know, but I don't think it has that causal link.
Thank you, Dr. Garrett. My name is Tommy. I'm a sports medicine doctor from Indonesia. I want to ask about your experience regarding to the environment, like a field, artificial, and maybe about the boots, in correlated with an overuse injury, I think. What is your experience?
With the artificial turf, there's certainly a micro-traumatic effect due to, and it's very individual. And I think there's some interesting examples clinically from rugby, lower back injuries, lower limb injuries, coming from micro-traumatic overuse injuries. And it's not necessarily the turf itself, it's that the players haven't grown up on that turf or haven't adapted to that turf. And so when initially rugby moved to artificial turf in certain sports, the incidence of lower back, of kind of shin splint type injuries, maybe in junior players, Osgood Slatteris, these sorts of things, was fairly high. But it was because they weren't training in that area, grass and artificial. Nowadays, it's much more variable. Athletes are training in artificial, athletes are training on natural turf at the elite end of the game and at the community level of the game. So I think it's become more the opportunity to adapt and develop your landscape of experience reduces that micro-traumatic event so your biological system can cope with it.
About the boots, any like as we know in running shoes there is a heel drop or maybe something in the outsole. In football boots, do you have any experience regarding the overuse injury?
Not so much with the boots, unfortunately. Not so much. I mean, the players at the elite end tend to have their own boots, as the previous question alluded to, and it tend to grow up and adapt into certain styles of boots. But certainly, I think more of a macro acute level of injury occurs with the boots when they are misused. So, for example, players, particularly in rugby, where you have certain players have longer studs, and their ability to embed into the ground causes issues around torsional rotation of the lower limb. Those are the issues. I'm not sure there's much on the micro traumatic events related to the boot itself. But that's only because I don't know. It could be.
Okay, thank you.
Thank you.
Regarding the pink shoes, I think this I got the answer. It's a trend and a catching because when I attend this conference, I already wear the pink shoes also. Thank you.
Thank you.
Okay, thank you for the question. Is there any question from the floor, please? Thank you. Professor Hirose from Waseda University.
Thank you very much, Dr. Garris. Very, great talk. So, your, research association with, bias and then perceived performance very makes sense to me. So that in this regards, I want to ask you about, fatigue, perceived fatigue, and then bias toward the, environment. So do you have any, idea about this in your expertise?
Could you repeat the question? Sorry.
Yeah, I want to know about the relationship or the association between the bias toward the environment, like artificial turf, and then perceived fatigue.
So the bias that the player has and its relationship to passive fatigue. Yes, it's an interesting question. I think from what we found with the artificial turf, the players arrived. If you would sit down with the players before and say, what would you rather play on, artificial or natural turf? Everybody would choose natural turf, particularly at the elite side of the game. In terms of fatigue, I think it comes back to the question from the other gentleman that if you've not got that ability to adapt, the fatigue that occurs then will increase because of you're constantly searching as a performer for the movement solutions that are going to allow you to achieve the performance goal and adapt to this surface. And if you've not got the ability to adapt, you're searching for so you're psychologically fatigued, you're physiologically fatigued, and because you've not adapted. And it's physical, it's like the training principles. Specificity of training, we need to train on what we're going to compete with. And if we're going to compete on artificial turf, we need to train on artificial turf and natural turf. And it becomes difficult if you've got a game on a Tuesday on artificial and the following week on natural, and then you're in Arsenal on the next day and it's a real challenge. And yeah, it's a brilliant question.
So I think I will still have one quick question, if anything would like to ask.
Very much. I'm from Sri Lanka. I just wanted to know now, do you have any recommendations for especially for the soccer players, the frequency of using these normal grounds as well as the artificial, the gradient 3D ground? Because sometimes, playing more on 3D grounds can use to the same system, but it is not happening in the, the real scenarios. Do you have any recommendation, maybe how frequency that you should change this surface training?
It's a good question, and I think FIFA, when they brought out the artificial turf, they had a recommendation that if you are playing on an artificial turf, you need to have at least an hour before the game to get used to it. And I mean, where that comes from, I don't know. It's, that's about short-term adaptation. I don't think there's a black and white answer to your question in terms of what's the recommended time that you spend on a surface, because it depends on where you're competing, on where you're playing. So if you don't ever play on artificial turf, then it would make sense for you to train and physically prepare yourself on the turf that you're on, natural turf. But if every third game is on an artificial turf, then within your physical preparation, your prehabilitation, you need to have that incorporated into your normal training regime. So rather than having it as a separate thing that you do all together, it needs to be just a natural part of the coach and coach and strength and conditioning coach and clinician to work together to come up with a program for those athletes. And it needs to be specific for those athletes. So it's difficult to come up with and say it needs to be 30 minutes every other day on an artificial turf, because it's so dependent upon the individual and the environments that we're competing in.
Yeah. It also depends on the adaptability of the athlete itself.
Absolutely. And if you've got, so we're trying to profile athletes to say you're a good adapter, you're not a good adapter. And it's not about that turf is better than that turf, it's your ability to adapt. You're going to have to compete on that anyway. So if you can identify those people that are not good adapters, then it gives you an opportunity to have some form of intervention. What the best intervention is another set of questions. But it's about, it's a really interesting topic, and I'm kind of just at the start of that in the elite football now, and it's interesting.
Okay, we run out of time.
Okay, thank you very much. I think we've run out of time. So thank you very much, Professor Gareth Irvin, and all the audience for all the good questions. Thank you very much.
Thank you.